Okay, indefinite interlogarithmic function. So just like in our derivative, we have the form derived, okay, formula derived using the inverse process of the derivative on those formulas for the derivative of exponential and logarithmic function. So I have 5 important formulas here, and we want to remember this. The first one, if you are integrating b to the ax with respect to x, so b is the base of the logarithmic, exponential function, ax, that is the exponent, and you can see that that exponent is the composite function because b is the outside function, right, exponential function, and the inside function is ax. So ax is the inside function of that composite function. Now, the integration of b to the ax is b to the ax over natural log b, okay? Because the integration of b to the x will be b to the x natural log b, and we are dividing by the derivative of that ax, and the derivative of ax is a. So that's why it becomes 1 over a natural log b times b to the ax. Because it is the indefinite integral, we need that c at the end. Same thing with the second one. Integration of e to the ax. You know that the derivative of e to the ax is e to the ax multiplied with the a, right? So integration of e to the ax is e to the ax, divide by the derivative of ax, which is a, so 1 over a. Integration of e to the x plus c. So those 3 are the formulas for the integration of exponential function. As you can see, first 3, these are the integration of exponential functions. You can write it down. Integration of exponential functions. Now the last 2, these are the formulas for the integration of logarithmic function. This is the general log function. See, log with base b of x, right? That is equal to 1 over natural log b. So that comes from the base change formula. And then integration of log x will be x log x minus x plus c. That's why the 5th one, integration of natural log x is x log x minus x plus c. So these 2 are the integration formula for logarithmic functions. So these are integration of logarithmic function. And in next couple of examples, we are going to use these formulas. Okay, here is the first example. We have to evaluate these integrals. Remember, we have the exponential functions in these 2 examples. If you look at the first one, we have e to the sine x, right? And we have e to the sine x divided by secant x dx. Remember, the only technique that we know so far for integration is the reverse process of derivative. That's one thing, right? If we have a direct formula there, reverse process. If not, the other thing we know is u substitution, right? We have the formulas, but we can still use the u substitution. So if you look at the first one, what I can see is, I see that this question is same as, let me write underneath. We have secant in the denominator. So 1 over secant is cosine, right? It's cosine x times e to the sine x dx. So we can rewrite the question like that. We have not changed anything because we have secant in the denominator, which is same as 1 over secant. Reciprocal of secant is cosine. Because by doing this, what I get is I got the product, right? I got the product. This is the composite function. E to the sine x is the composite function. Inside function is sine x. What is the derivative of sine x? Cosine x. It is also there. That means this one is ready for u substitution, right? And your inside function is sine x. That means u equal to sine x. So let's do that. Let u equal to sine x. What is the derivative of that? Du over dx is how much? Cosine x, right? And then if we multiply on both sides by dx, we get du equal to cosine x dx. Let's substitute then. This is equal to integration of, first I'm going to substitute this one here, e to the sine x. That becomes e to the u. And the remaining part is cosine x times dx. And from our side work, we know that cosine x times dx is a du. And see how simple is that? Integration of e to the u with respect to u is e to the u, right? Because derivative of e to the u is e to the u. So that is equal to e to the u plus c. And that's my answer, but not the final answer. I need my answer in terms of x. So I'm going to substitute the value of u. And u is equal to sine x. So final answer becomes e to the sine x plus c. E to the sine x plus c. Any question on that? Why we are not keeping the cosine in the denominator? Okay, the reason is if I keep cosine in the denominator, I mean secant in the denominator, right? If I keep secant in the denominator, when I do the differentiation, I'm not going to get the secant. But remember, we have secant in the denominator. Secant in the denominator, meaning of that is 1 over secant, right? And 1 over secant is cosine, not 1 over cosine. That's why cosine is in the numerator, not in the denominator. Does that make sense? Okay. Any other question? Yes.
Why does du get rid of cosine?
Du, this one?
Like u to the u, like why does cosine?
Which, are you talking about this step? Second step?
Well, du is cosine x dx. Why does cosine x dx just go away?
Cosine x dx, I'm writing that as du.
Yeah. Why does it disappear?
It's not disappearing. It's telling us that du, meaning of that du and the integral sign, these two are the operator. This integral sign in front and du are the the operator. They are saying that you are integrating du, e to the u with respect to u. That's what they are saying. So this is full notation. This one, the integral sign with du is the notation for integration. Like for derivative, we have d over dx. So along with that du, this integral sign in front, these are the operator. These two things are telling us to integrate. So when you integrate, what do we get? We get that. We don't need integration anymore. So we drop those two. Like in the limit, as long as we have that x, we write the limit in front, right? Once we are done with the x, we leave the limit just like that. Any other wonderful question like that? No? Okay. Let's go to B for beautiful then. Okay, in B, what do you see? If you look at B carefully, we have e to the x over 2 divided by e to the x over 2 plus 1. If you look at this carefully, in the denominator, we have e to the x over 2 plus 1. I can consider that as the u. If I consider that as the u, I should look for the derivative of e to the x over 2. In the denominator, I have e to the x over 2 plus 1. What is the derivative of e to the x over 2 plus 1? Remember, I can write like this. Derivative with respect to x of e to the x over 2 means e to the half x plus 1. E to the x over 2 plus 1. Denominator, right? Denominator is e to the half x plus 1. If I want to find the derivative of 1 is 0. Derivative of e to the half x will be e to the half x and you multiply by half, right? So that will be equal to half e to the half x or x over 2. So now what I am trying to do here is the derivative of e to the x over 2 plus 1 is e to the x over that half here? No. So I'm going to multiply by half there. Okay, I'm going to multiply by half there. If I multiply by half here, I can multiply outside by 2, so that 2 times half is 1. 2 times half is 1, right? So I can do this. Then we can easily perform the u substitution. U will be our denominator. Okay, let u equal to e to the x over 2 plus 1 and du over dx. The derivative of e to the x over 2 plus 1, we did that on the top of the board there. You can see that is half e to the x over 2. If you multiply on both sides by dx, then it will be half e to the x over 2 dx. Then you can do the substitution. So that 2 is outside, you can keep as it is. In the denominator, it becomes u, right? E to the x over 2 plus 1 in the denominator, that's a u. Now in the numerator, everybody look at the screen. In the numerator, we have half e to the x over 2 dx. But we know that half e to the x over 2 times dx is a du. So for all this in the numerator, we can write that as du. We can write that as du. U substitution, right? So 2 is outside, we can keep as it is. And then we have integration of 1 over u. We know that the derivative of natural log is 1 over u. So that becomes natural log. I can write this as natural log of absolute value of u plus c. We need absolute value because we don't know whether u is positive or negative. If we know that it is positive, we can just leave it without the absolute value. That's my answer, but not the final answer, because I have to resubstitute the value of u. So if I resubstitute the value of u, this is what happened. This is equal to 2 natural log of the absolute value of u is e to the x over 2 plus 1, then plus c. Remember one thing, e to the x over 2, exponential function is always positive, right? It cannot be 0. It's always more than 0. A number more than 0 plus 1, this quantity inside the absolute value is always positive. If that is always positive, do I need the absolute value? I don't need the absolute value. So in next step, I have to leave the absolute value and write it as natural log of e to the x over 2 plus 1 plus c. Yes, because you have to, because while changing this absolute value to parenthesis, you are demonstrating the understanding of the argument of the log. So you have to go from here to here to get that full points. Yes. That is required there. Okay, I am going to show you one important technique here. I'm going to solve this b again using a different method. You can write it separately somewhere in your notebook, but I'm going to show you b using a little bit different method. And also I'm going to give you a technique there. So in b, what we have seen is we have e to the x over 2 divided by e to the x over 2 plus 1 with respect to x. We saw that the derivative of denominator is not quite there in the numerator. If it was half, then it will be the derivative of denominator in the numerator, right? So what we did was we multiplied there by half. So let me show that step there. We multiplied there by half and 2 outside. Now, one very important technique that you need to remember in integration is, okay, this 2 is a constant. I'm going to write as it is, 2. If the derivative, listen carefully, if the derivative of the denominator, is in the numerator, like in this one, the derivative of denominator is now in the numerator, right? If the derivative of denominator is in the numerator, the value of the integral is the natural log of let me write it down. It is equal to the natural log of the absolute value of denominator directly. Which is equal to 2 times the natural log of that quantity is positive. So I don't need that absolute value there, plus C. So important note for you is this. Note that if you have an integration function and you have some function in the denominator, but its derivative is in the numerator, then this is equal to natural log of absolute value of denominator plus C. Very, very important formula or technique. One more time. If the derivative of denominator, see, f of x is the denominator. The derivative is f prime x. If the derivative of denominator is in the numerator, then the value of integral is equal to the natural log of the denominator plus C. Okay, very important technique for you. Okay, let's go to next example now. These two involve the exponential functions there, as you can see, right? Both are exponential functions. And in both of these exponential functions, if you look carefully, there is one interesting thing. In both of them, your inside function is a linear function. Do you see that? 4x there. 4x is a linear function. And here also 3x plus 1 is a linear function. Meaning of that is when you divide directly by the derivative, it works there. But we have the formula. If you remember, we had the formula. What was that? If you go back to your notes and check it, we have integration of b to the ax with respect to x is equal to b to the ax divided by how much? A natural log b, is that right? Plus c. That was the formula. Okay, I wrote all the way on the top. Yeah, so it is b to the ax over a natural log b. Do you see it now? That is the formula. So we are going to use that concept to integrate these two. So basically what we have done is, see, we have b to the ax. So that part as it is, b to the ax as it is. The base of the exponential function is b here, not e. If it is anything other than b, you divide by natural log of b. That's what we have. And then we are dividing by the derivative of ax. Derivative of ax is a. Okay, so you follow the exact same procedure here. So this one will be integration of, for a, we have integration of e to the 4x dx. That is equal to, not e, why I'm writing e, that's 3, right? 3 to the 4x, 3 to the 4x dx. That is equal to 3 to the 4x divided by natural log 3 multiplied with the derivative, that is 4 plus c. Done. That's it. There is nothing we can simplify, right? You can multiply these to get a decimal number, but that's a decimal, not accurate, right? But this is accurate. So what we did, 3 to the 4x as it is, because this is not e, we divide by natural log 3 and we divide by the derivative. Same thing with the next one. So in b, we have the integration of e to the 3x plus 1 dx. This one has e. So it will be e to the 3x plus 1. You can divide by log e if you want, and then multiply by 3. Then plus c. If you use the same formula, what do you do? E to the whatever is there, we write as it is, right? And you can see in our formula, we divide by log B. So here, in place of base, we have E, so log E. And we divide by the derivative of this function 3x plus 1, which is a 3. But log E is how much? 1. So it becomes 1/3, right? It just becomes 1/3 e to the 3x plus 1 plus c. Are we good with that? Any question on these two examples, A and B here? No, all good? Okay. Look like we did a lot of integration today, right? Yeah. We have a few more, maybe these two. Okay, we'll just do these two. Okay, these two are the integration of the logarithmic functions. So if you remember the formula, integration of log with any base b, right? Log with any base b of x, or you can also write ax, it is up to you, but I'll write x here. I'm talking about this formula here. Let me go back and show you. This one here. Log b with x, okay? Log with base b of x. It will be x natural log x minus x, and you divide by log b, okay? So this is equal to x natural log x minus x over natural log b plus c. That is the formula. Remember, this is the formula. This is the formula because we have x here. Look at the board. We have x here, right? If this is something other than x, if that is a linear function like 5x plus 1 or 3x minus 5, we have to divide by the derivative. Okay, we have to divide by the derivative over here. So remember that one, and then let's do it. So in A, we have integration of not natural log, log with base 3 of 5x plus 1 with respect to x. So that is equal to, if you look at the formula, we have x log x, but in place of x, we have 5x plus 1. 5x plus 1, natural log 5x plus 1, and then minus x, so minus 5x plus 1, divided by the natural log of the base. Also, you have to divide by the derivative. Does that make sense? Because it is x log x. So 5x plus 1 is x log x, then minus 5x plus 1. You divide by log b, so log 3. But we have not x, but 5x plus 1. So we have to divide by the derivative of 5x plus 1, which is 5. Okay? And there is nothing we can simplify after that. Probably you can factor 5x plus 1, but it will not give you anything new there. So it's okay to leave it there, plus c. But the next one, if you look at b, b has the natural log. Look here, if here is natural log, what happened? If here is natural log x, then we don't need this one, right? Because this log b comes from the base change formula. So if it is just the natural log, we don't need this part, just the numerator. So for the second one, because it is the natural log, let me write it down. Integration of natural log of 3x minus 5 with respect to x is equal to x log x. X is 3x minus 5. Natural log 3x minus 5, x log x, minus 3x minus 5. Divide by the derivative, divide by 3, plus c. That's it. So we are using the formula directly in these two examples for the logarithmic function. Any question on these two?
How are you getting like 5 ln 3 and 3 in like the denominator?
Are you talking about this 3 and 5? Because your argument of the logarithmic function is 5x plus 1, a linear function. Do you see that? Both are linear function. So we have to use the chain rule for integration. That is, you have to divide by the derivative of the inside function. So derivative of 5x plus 1 is a 5. We divide by 5. Similarly, in the second one, derivative of 3x minus 5 is a 3. So we are dividing by 3. Because we are using the chain rule for integration. So we are dividing by that inside function. Okay.